Welcome to the fourth video on mathematical formulations of microbial growth, and the second one about thermodynamics. In our previous class, we learned about energy and how we can estimate the energy of any given redox reaction. We learned that this energy is a function of the strength or weakness of the involved electron donor and acceptor. We compared the energy released in the catabolism when glucose is oxidized to CO2 or glucose is fermented to ethanol. And we reflected, based on experimentally derived growth yields, how the amount of energy released in the catabolic reaction impacts the final growth yield. In this class, we will learn a thermodynamic-based framework, a mathematical tool to estimate, theoretically, the yield of any growth system. And this will serve as a first approximation to downstream calculations. To start, I would like to begin from the second law of thermodynamics. We learned in our previous class that for a reaction to be spontaneous, the entropy of the universe has to increase. We also learned that under very reasonable assumptions for biological systems, such as constant temperature and constant pressure, we can write the same second law of thermodynamics in a form that takes into consideration the sole system we are interested in. For this, we defined a new thermodynamic potential as the Gibbs free energy. What we are interested in is a change in Gibbs free energy at constant pressure and constant temperature. And this is quantified by a change in the enthalpy, the heat, and the change in entropy with a negative sign and scaled for the temperature at which the reaction occurs. To comply with the second law of thermodynamics, in other words, for a process to be spontaneous, the delta Gibbs free energy change has to be negative. Now, the impact of the two terms, enthalpy and entropy, may differ between reactions. I invite you here to reflect on the fact that when we will calculate the energy involved in glucose respiration, you will see that most or the majority of the delta G comes from a change in enthalpy. When we will analyze glucose fermentation instead, you will appreciate that once you correct for the pH of 7, that only half of the delta G comes from a change in enthalpy, with the rest coming from an increase in entropy of the system. Glucose, a more complex substrate, is split into ethanol and CO2. An example that I will not have time to discuss with you, but I invite you to develop yourself, is the production of methane from acetate. In that case, if you calculate the delta G and the delta H, you will notice that the delta H is even positive, so negatively contributing to the spontaneity of the reaction. However, the involved increase in entropy is significantly higher, to the point that delta G becomes negative and the reaction is thermodynamically favorable. For those of you who are interested in getting a little bit more deeper reflection on these aspects, I provide you here with a very interesting reference. And now it's time to start the second lecture on thermodynamics, and we start from equilibrium thermodynamics. We speak about equilibrium thermodynamics when we refer to reactions that occur at almost instantaneously or at rates that are significantly faster than the ones of the biological processes we are interested in. Equilibrium refers to a situation where the driving force for the reaction to occur in one direction or the opposite is minimized. In other words, the delta G1 equals 0, where delta G1 is the delta G0 corrected for the actual activity or concentration for diluted system of the products and the substrates. Now, under this assumption, we can rewrite the equation and express the delta G0 as a function of this correction term. And this ratio here is how commonly we define the equilibrium constant of any reaction. That's why we rename this ratio as the K equilibrium. We can now rearrange again the equation and obtain the expression of the equilibrium constant of a given reaction as a function of the delta G0. Now, to make this concept a little bit more concrete, I took an example very relevant for biological processes, namely the carbonate system. We here assume a gaseous phase with a given partial pressure of CO2 to be in equilibrium with the liquid phase. Now, CO2 distributes at equilibrium between the gaseous phase and the liquid phase according to Harris' law, and this is Harris' constant. And once dissolved in the liquid, carbonic acid star as a sum of carbonic acid and primarily CO2 dissolved is in equilibrium with bicarbonate, and protons are in equilibrium with water. If we write the corresponding equations, CO2 dissolves in the liquid, carbonic acid or dissolved CO2 is in equilibrium with bicarbonate, and bicarbonate in equilibrium with carbonate. We can now define, as we said before, the equilibrium constant as the ratio of the activities or concentrations normalized by reference concentrations of the products and the substrates. For the CO2, we express it in partial pressure. The subsequent constants can then be expressed as a function of the preceding ones, as described here. With this in mind, we can now calculate the actual value of these constants and, as a result, the concentration at equilibrium of the corresponding species. For this, we go again to our spreadsheet, and as we did for the pH, where we refer to the concentrations we are interested in and changed only the protons, now what we want for the carbonate system is to have all concentrations at 1 mole per liter at a pH of 7, and then based on the assumed 0.3 atmospheres of CO2, we want to know what are the equilibrium concentrations of carbonic acid, bicarbonate, and carbonate. To do so, we define the stoichiometry of the equilibrium reactions, namely, CO2 in the gas is in equilibrium with carbonic acid in the liquid. Carbonic acid in the liquid is in equilibrium with bicarbonate, and bicarbonate with carbonate. We balance all the equations for oxygen, hydrogen, and charge. As they are full reactions, there should be no free electrons. We check the mass balance, and finally, as we did in the previous class on thermodynamics, we calculate the delta G0 as a sum product of this vector and this vector. Once we have the delta G0, as we have seen before, we can calculate the equilibrium constant. In this case, as it's in equilibrium between gas and liquid, it is the Harry constant. Once we have this value, we can directly calculate the concentration of carbonic acid, a sum of carbonic acid and dissolved CO2, in the liquid for this partial pressure. From this, we can calculate the following constant, and finally calculate the bicarbonate concentration, where also the pH plays a primary role, as you see here. Finally, we can also calculate the carbonate concentration in the liquid, again as a function of the concentration of protons. With this, you might want to stop the video and proceed with the calculations yourself. And if you are now back, these are the results that you should have gotten in terms of constant and in terms of corresponding equilibrium concentrations. Now we can of course make a check and make sure that the assumptions that we made of equilibrium, so delta G1 equals 0, is respected. And so this is the case. We can calculate delta G0, and as these are the equilibrium constant, then the reaction is at equilibrium. Equilibrium concentration, sorry, then the reaction is at equilibrium. Once we have these concentrations, we can finally calculate the delta G1 for our glucose respiration and glucose fermentation to ethanol. Now with this, if we go back to our candy experiment, where we wrote the equation of glucose oxidation to CO2 or to bicarbonate, we left our calculations here, where the delta G01 were starting to converge, but not yet. If now you stop this video and want to calculate the delta G1, I will wait here just a little bit. Now, if you proceeded with the calculations, these are the numbers that you should have gotten, showing that if you consider the actual concentrations of all the involved compounds, it doesn't really matter which form you use in your stoichiometric equation. Of course, for such a very strongly energetic reaction, this might not play a major role, whereas if you work at close to thermodynamic equilibrium, where the energy generated in the catabolism is barely sufficient to sustain life, then all these corrections of the concentrations play a significant role. Now finally, we reach the final part of these two lectures on thermodynamics, which is about non-equilibrium thermodynamics, which is in essence what life is about. In our first lecture about thermodynamics, we learned that life requires a constant driving force, a constant input of energy. This is why we speak about non-equilibrium thermodynamics. Delta G cannot be 0. If we look at the scheme we have been working with throughout these classes, a cell requires a constant flux of substrates which are catabolized to produce the energy to then maintain the cell and synthesize new biomass. We learned together that we can combine these two stoichiometries if we know and experimentally determined growth yield to then derive the full stoichiometry of the metabolism. This, however, might not always be the case, especially if you study new metabolisms. Literature might not be available, and also going to the lab might be challenging at times. So a lot of research has been dedicated in the last decades to derive theoretical approaches to estimate, at least as a first approximation, the growth yield of any microbial system. The method we will be discussing here is a thermodynamic-based framework that was developed in Delft by Seth Heinen based on an immense amount of literature data on different metabolisms that was compiled by the authors and then interpolated to provide a general approximation of growth yield. To understand what we're speaking about, I go back a little bit to the stoichiometry class. In this class, we define a metabolism as the sum of the catabolic and anabolic reactions with two coefficients. We assume one coefficient to be 1, such that the metabolism is expressed per mole biomass produced, and the lambda cut under these assumptions tells us the efficiency of the metabolism, namely how many times we have to run the catabolism to produce 1 mole of biomass. We will now take a look at this same equation from an energetic perspective. We know from the first law of thermodynamics that we can make energy balances, and this is what we will do. So in the first class of thermodynamics, we also learned how to calculate the Gibbs free energy change associated to the catabolism and the anabolism. The catabolism generates the energy, and the anabolism in some cases has a slightly positive and in some cases slightly negative delta Gibbs free energy change. However, this delta Gibbs free energy change does not take into consideration the complexity of a biomass. All the proteins that have to be folded and maintained active, but only considers the stoichiometric composition of the biomass. Therefore, we now have to realize that the catabolic energy not only has to compensate for the energy invested in the stoichiometric composition of the biomass, but also in building all the complexity. For this reason, the energy equation the energy balance does not equal 0, but equals the energy that is dissipated to create the complexity of the biomass from its more simple constituents. The method we will learn here is targeted to estimate this energy consumption here. And it will tell us also how efficient the metabolism is. The lowest this energy is, the more efficiently the metabolism is able to build the biomass from its elemental constituents. This method is called Gibbs free energy dissipation method, was developed in Delft, and is generally applicable to all chemotrophic growth systems. Has a direct relationship with the second law of thermodynamics. This part of the equation here has always to be negative. Delta G has always to be negative for a process to be spontaneous. So any full metabolism has to have a delta G that is negative. Importantly, especially for new metabolism, it does not require a metabolic knowledge or a detailed biochemistry. You might not know it when you start studying, but simply the electron donor, acceptor, and carbon source involved, which is basically what we have been dealing with in the last lectures. And it has no methodological flows. And for those, I direct you to the first published paper on this method. What is important is that what the authors, based on this incredible amount of literature data, derived is that this Gibbs free energy dissipation depends exclusively on the carbon source used and the anabolic electron donor. So based on this knowledge, we can now calculate this number. And as we did ultimately in the stoichiometry class, we will be able to calculate the lambda cut and finally the full metabolic equation. So by interpolating all the data that was collected, the authors propose two equations to calculate the delta Gibbs free energy dissipation. The first one is applicable to basically all metabolisms that do not require reverse electron transport, which are all metabolism based on organic carbon sources and autotrophic metabolism with strong electron donors. In this case, we can apply this equation, which is only a function of the number of carbons of the carbon source and the degree of reduction. In cases where CO2 autotrophs is the carbon source, but the same metabolism also relies on a poor electron donor, electrons need to be energized to be able to fix CO2 and to reduce it to biomass. In this case, reverse electron transport is needed, energy is consumed, and thus the energy dissipation is significantly higher. Now, just for completeness, what we define as degree of reduction, the electrons released per carbon atom upon full oxidation of CO2 of the carbon source, number of carbons of the carbon source, C, mole per mole carbon source, and reverse electron transport, which is essential for autotrophs with poor anabolic electron donors. If we plot this first equation as a function of the degree of reduction and per carbon number of carbons, what I want you to appreciate first is that these curves reach a minimum that it goes towards a degree of reduction of 4 electrons donated per carbon mole of the carbon source and is reduced at higher number of carbons. So what we need to know is that building blocks of biomass contain 4 to 6 carbons and have a degree of reduction on average of 4. This means that the closer the carbon source is to the building blocks of biomass, the least energy will be consumed to produce this biomass. And for this very reason, glucose is an excellent carbon source. 6 carbon atoms and 4 electrons more or less released per carbon. Well, actually 4 electrons released per carbon. Now, if this might feel still a little bit abstract, let me give you a concrete analogy. So let's assume you are asked to build this wood cabin that I drew with AI, or AI drew for me. You might have the chance and opportunity to use already cutted wood. Or you might have the pleasure to walk through a forest, but be forced also to use this wood, which needs to be processed first in this shape and then finally into the cabin wood. In this case, it's clear that more energy needs to be invested. In terms of tools that you might have available, I have here to thank my brother-in-law, Sean, for letting me take a picture of his tools. You might be lucky and have access to electrically powered tools to build your cabin, or you might be left with only manually operated tools. If we look at the analogy with the cell, we can think of the cell as the wood cabin and the carbon source as these two types of food. The closer you are to the shape of food you need is like having glucose, the least energy you need to invest. Instead, if you have to start from the forest, like starting from CO2, you need to invest much more energy to produce the cell. Even more, if you have electric tools, like strong electron donors such as glucose or hydrogen for autotrophs, for example, then the energy is significantly less than if you are left with poor electron donors in the anabolism, such as nitrite for Anamox. In this case here, the energy required is the maximum. Now, with this analogy, before moving on, I also would like to highlight that once the cell or the cabin is built, should you wish to burn it, the energy released from this cabin or from the equivalent of amount of wood used to build it is definitely the same. So all the energy you spend to build this complexity is the energy you dissipate. With this analogy, I hope now you can look at this equation from a different angle. And by just rearranging this equation as we did in the stoichiometry class, we can now derive the lambda catabolism, which, and here I would like to highlight this, depends on the delta G of the anabolism, the dissipation one we calculated before, and the catabolism. The stronger your catabolism is, the more energy It releases the least amount of times you will have to run your catabolism to produce 1 mole of biomass, because the delta G catabolism is in the denominator. In analogy again to what we did in the stoichiometry class, we can now derive the growth yield based on the lambda cut we derived. Importantly, this growth yield here is a maximum growth yield that will always exceed the experimentally derived one because maintenance is not considered. This yield does not account for the amount of substrate that is consumed only to produce energy to maintain the cell. Now, with this in mind, how does this look if we implement this in our spreadsheet? Well, we have our glucose respiration, glucose fermentation, and the anabolism on glucose, which is what we assume to be common to the two metabolisms. We need to find a way to link catabolism and anabolism. How we do it theoretically, we consider the number of carbons of the carbon source, the degree of reduction, electrons released upon full oxidation of the carbon source per mole of carbon, and we can derive now the delta G dissipation just by implementing this equation. What I want you to highlight, to notice here, is that the delta Gibbs free energy dissipation is the same whether we look at respiration or fermentation, because it only depends on the anabolic pathway. Now, finally, we can calculate the lambda cut. And here is where we have the impact of the energy generated in the catabolism, significantly higher if we consider the correction for pH for glucose respiration compared to fermentation. This is then directly reflected in the yield that we will obtain. And then, once we have the lambda cut, we can calculate the full metabolism and derive the yields. Here, I would like to highlight the fact that in the example in the stoichiometry class, where I used experimentally derived yields, I actually use these values here. They will not coincide in reality, but they get quite close. What is important and doesn't matter is the fact that either experimentally, either now you know how to do it from a theoretical perspective, you can derive the metabolic yield of biomass growth on the substrate. So now we can conclude this part by stating that not only we can use experimentally derived yields, but also maximum yields derived from thermodynamic-based frameworks to couple catabolism and anabolism. This yield will always be higher than the observed one because the maintenance is not considered. And this is exactly what we will be doing, at least in part, of the kinetic class that follows. So with this, I thank you for your attention, and I see you in the next video.